In the outer solar system, a mysterious pattern emerges. Beyond Neptune, icy bodies called trans-Neptunian objects, TNOs, move in synchronized elongated orbits, defying known gravitational influences. This alignment, dubbed the disturbance, suggests an unseen force and challenges our understanding of the solar system's evolution. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it on X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. The story began with Sedna in 2003. At 76 AU from the Sun, its stable yet eccentric 11,400-year orbit implies unknown influences. Sedna avoids the giant planet's pull, and though linked to the inner Oort cloud, its origin remains a mystery. Further discoveries deepened the puzzle. Biden, 2012, VP-113 in 2012, and the Goblin, 2015 TG-387 in 2015, share highly eccentric stable orbits with perihelia clustered in one direction, an anomaly unexplained by known planets. The Goblin's orbit extends to 2300 AU. To explain these orbits, astronomers proposed Planet 9, a hypothetical world 10 times Earth's mass, orbiting between 400 and 800 AU. Its gravity could account for the TNO's alignment, offering clues to the solar system's chaotic past. However, its predicted faintness makes detection challenging. The upcoming Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory could provide answers, mapping the sky with unprecedented depth. Observation. Sedna and other distant TNOs align in a pattern unexplained by known planets, suggesting an unseen influence like Planet 9. Interpretation. Planet 9 offers a compelling explanation for the TNO's alignment, potentially solving the disturbance and revealing insights into the solar system's formation. Speculation. Confirming Planet 9 could redefine our understanding of the outer solar system and raise questions about undiscovered planets elsewhere. The search continues, driven by the possibility of uncovering a hidden chapter in our solar system story. Each new TNO discovery brings astronomers closer to solving the mystery. Part 1. The Lonely Wanderer. Sedna's discovery was a wake-up call for astronomers. Its orbit was unlike anything they had seen before, a frozen wanderer moving through the frigid emptiness of the outer solar system. While most objects beyond Neptune are shepherded by the giant planet's gravity, Sedna is untouched by Neptune's influence, its motion governed by forces that remain mysterious. Its closest approach to the Sun, known as perihelion, is more than twice Neptune's distance from the Sun, approximately 76 astronomical units, AU, away. To put this into perspective, if the Sun were scaled down to the size of a single pixel on a smartphone screen, Sedna's orbit would extend far beyond the edges of the device. At its farthest point, known as aphelion, Sedna ventures out to a staggering 937 AU, a distance so vast that it takes light roughly 10 hours to travel from Sedna to the Sun. This isolation raises questions that have haunted astronomers for decades. Did a passing star long ago nudge Sedna into its current path, a cosmic interloper disrupting the delicate balance of the early solar system? Or is it a relic from the solar system's chaotic early days, when planets were still migrating and scattering objects in all directions like children kicking up dust in a playground? Sedna's surface is a deep reddish brown, a color that hints at a rich organic chemistry forged over billions of years of exposure to cosmic radiation. Its slow, 11,400-year orbit means it spends most of its existence in the unexplored depths of the outer solar system, where temperatures plunge to 240 degrees Celsius. At such extremes, water ice, which likely makes up much of Sedna's composition, behaves like rock, rigid and unyielding. Yet, Despite these harsh conditions, Sedna's surface may harbor complex molecules, the precursors to life, frozen in time. The reddish hue is thought to result from tholins, complex organic compounds created by the irradiation of simpler molecules like methane and water. These tholins are not unique to Sedna. They have also been observed on other distant bodies, such as Pluto and the Kuiper Belt objects, suggesting a common chemical process at work in the outer solar system. For years, Sedna remained an oddity, a single piece of a puzzle that didn't yet exist. Its discovery in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz was initially met with skepticism. How could such a distant, isolated object have formed in the first place? But in 2012, another object was discovered, 2012 VP-113, nicknamed Biden after the then Vice President of the United States. Like Sedna, its perihelion is far beyond Neptune's reach at 80 astronomical units. This object, even smaller and fainter than Sedna, was found by the same team that had discovered Sedna nearly a decade earlier. Two objects with similar characteristics suggested a pattern, not a coincidence. The outer solar system, long thought to be a quiet graveyard of icy debris left over from the formation of the planets, suddenly seemed far more dynamic. Something was organizing these distant orbits, but what? The discovery of Sedna and 2012 VP-113 forced astronomers to confront a startling possibility. The outer solar system might not be the lifeless void it appeared to be. Instead, it could be teeming with undiscovered objects, their orbits shaped by forces yet to be understood. These objects, collectively known as extreme trans-Neptunian objects, ETNOs, are so distant and dim that they push the limits of modern telescopes. The Dark Energy Camera, DCOM, mounted on the Victor M. Blanco telescope in Chile, one of the most powerful tools for detecting such faint objects, has only scratched the surface of what might lie beyond Neptune's orbit. Since 2012, additional ETNOs have been identified, including Lela Kuhanwa, 2015 TG387, and 2015 RR245, each with orbits that defy conventional explanations. Leleakuhonqua, for example, has an aphelion of over 2,000 AU, placing it among the most distant known objects in the solar system. Observation: the orbits of Sedna and 2012 VP-113 are not just unusual, they are mathematically improbable. Simulations of the early solar system suggest that objects like these should have been ejected entirely or captured by Neptune's gravity long ago. Yet here they are, defying expectations. Their orbits are stable and highly elliptical, stretching out into the vast emptiness of the Oort cloud, a theoretical, spherical shell of icy debris that marks the outer boundary of the Sun's gravitational influence. This stability suggests that something is preventing these objects from being perturbed into different trajectories. But what could exert such influence in the outer reaches of the solar system, where the Sun's gravitational pull is weak and distant? The Oort cloud itself is estimated to contain trillions of icy bodies, but its structure and dynamics remain poorly understood. Speculation. One hypothesis proposed by scientists in 2014 suggests that a massive undiscovered planet, dubbed Planet 9, lurks in the outer solar system, its gravity sculpting the orbits of Sedna, 2012 VP-113, and potentially hundreds of other ETNOs. This planet, if it exists, would be roughly 10 times the mass of Earth in orbit at an average distance of 400 to 800 AU from the Sun. Its existence could explain not only the orbits of Sedna and 2012 VP-113, but also the peculiar tilts of other trans-Neptunian objects and even the slight wobble of the Sun itself. However, despite extensive searches, Planet 9 remains undetected, a ghostly presence inferred only through its gravitational footprint. Some models predict that Planet 9's orbit could be inclined as much as 30 degrees relative to the ecliptic, the plane in which most planets orbit, making it even harder to spot. Interpretation: the search for an explanation goes beyond Planet 9. Some researchers have proposed that the collective gravity of countless small, unseen objects in the outer solar system could account for the strange orbits of Sedna and 2012 VP-113. Others have suggested that a passing star or rogue planet in the solar system's infancy might have disrupted these objects, flinging them into their current paths. Still others have entertained more exotic possibilities, such as the presence of a primordial black hole lurking in the outer solar system, its immense gravity warping the orbits of nearby objects. Each of these theories carries profound implications for our understanding of how the solar system formed and evolved. For instance, a primordial black hole, if it exists, could provide clues about the conditions in the early universe when such objects might have formed. What if the outer solar system isn't as empty as we thought? This question, posed by Mike Brown in the wake of Sedna's discovery, has taken on new urgency in recent years. As telescopes grow more powerful and surveys of the outer solar system become more comprehensive, the possibility of discovering new etnos, or even Planet 9 itself, feels increasingly within reach. Each new discovery adds another piece to the puzzle, bringing us one step closer to unraveling the mysteries of the solar system's lonely wanderers. The upcoming Varus C. Rubin Observatory, set to begin operations in 2024, will conduct a 10-year survey of the entire visible sky, potentially uncovering thousands of new objects beyond Neptune. Its legacy, Survey of Space and Time, LSST, is expected to revolutionize our understanding of the outer solar system, mapping its depths with unprecedented precision. As astronomers peer deeper into the cosmic abyss, they are guided by a sense of wonder and curiosity that has defined human exploration for millennia. The search for Sedna's origins is not just a scientific pursuit, it is a journey into the unknown, a quest to understand our place in the universe. The outer solar system, once dismissed as a barren wasteland, now stands as a frontier of discovery, a realm where the laws of gravity and the echoes of the past intertwine. And at the heart of this frontier lies Sedna, the lonely wanderer, a silent sentinel awaiting the day when its secrets are finally revealed. Its reddish surface, scarred by billions of years of cosmic radiation, tells a story of resilience and endurance, a testament to the enduring mysteries of the cosmos. Part 2. The Aligned Orbits. In 2014, astronomers Chad Trujillo and Scott Shepard published a groundbreaking study. They had been searching for more objects like Sedna and 2012 VP-113, and what they found was astonishing. These distant objects weren't just far away, their orbits were aligned. Imagine looking down at the solar system from above. The planets orbit in a flat disk, each tilted slightly differently. But these distant objects were different. Their perihelia, the points where they come closest to the Sun, were all clustered in one region of space. Statistically, this shouldn't happen. If these objects were scattered randomly, their orbits should point in all different directions, unless, of course, something is organizing them. The discovery was akin to finding a hidden pattern in a seemingly chaotic system. The orbits of these distant bodies were not just aligned, they were also elongated, stretching out into the far reaches of the solar system. These elliptical orbits were far more extreme than those of the known planets, with some objects taking thousands of years to complete a single revolution around the Sun. Sedna, for instance, has an orbital period of approximately 11,400 years, while 2012 VP-113 takes around 4,200 years. The alignment of these orbits suggested a gravitational influence far beyond what Neptune, the outermost known planet, could exert. Trujillo and Shepard proposed a bold hypothesis. A massive undiscovered object could be gravitationally shepherding these smaller bodies into similar orbits. This was the first formal suggestion that something unknown, something far beyond Neptune, was shaping the outer solar system. But the evidence was limited. Only a handful of objects had been discovered, and the idea was far from proven. Still, the seed of a mystery had been planted. The possibility of an undiscovered planet, or even a small star, lingered in the minds of astronomers, sparking a new wave of exploration and debate. What we know: the orbits of these distant objects are aligned in a way that defies random chance. Their perihelia cluster in a specific region, and their orbits are extremely elongated, suggesting an external influence. The gravitational pull required to align these orbits would need to come from an object significantly more massive than Earth, potentially rivaling the size of Neptune or even larger. What we don't know: whether this alignment is caused by an undiscovered object or something else entirely. The exact nature of this hypothetical object, whether it is a planet, a brown dwarf, or something more exotic, remains unknown. Additionally, the precise mechanism by which this object could influence the orbits of these distant bodies without disrupting the inner solar system is still a matter of speculation. The idea of a hidden planet was not entirely new. In the 19th century, astronomers had predicted the existence of Neptune based on perturbations in the orbit of Uranus. Similarly, the search for Planet X beyond Neptune had been ongoing for decades, with notable figures like Percival Lowell dedicating years to the hunt. However, the alignment of these distant orbits introduced a new layer of complexity. Unlike the perturbations observed in the past, this pattern was subtle yet unmistakable, hinting at an object that was both massive and distant. Observational efforts intensified. Astronomers around the world began scanning the outer solar system with renewed vigor, hoping to find more objects that fit the pattern. The Outer Solar System Origin Survey, OSOS, for example, discovered over 800 trans-Neptunian objects, though not all exhibited the same orbital characteristics. Each new discovery added to the growing database of distant bodies, but the alignment remained consistent among a select group. This selectivity only deepened the mystery, as it suggested that whatever was influencing these orbits was doing so in a highly specific manner. Speculation began to run wild. If a massive object existed beyond Neptune, how had it remained hidden for so long? Some hypothesized that it could be a rogue planet captured by the sun's gravity, while others suggested it might be a primordial remnant from the early solar system. Still others proposed that it could be a brown dwarf, a failed star too small to initiate nuclear fusion. Each theory carried its own set of implications, from the potential for undiscovered moons to the possibility of a habitable environment deep in the outer solar system. The alignment of these orbits also raised questions about the formation of the solar system itself. If a massive object existed beyond Neptune, it would challenge traditional models of planetary formation, which suggested that the outer solar system should be largely empty. The presence of such an object would imply that the early solar system was far more dynamic and chaotic than previously thought, with planets and other bodies being flung into distant orbits by gravitational interactions. Interpretation: the alignment of these distant orbits suggests that the outer solar system is not as empty or static as once believed. The existence of a massive undiscovered object would rewrite our understanding of planetary formation and the solar system's evolution. It would also open the door to new questions about the potential for life in the outer reaches of the solar system, where conditions are vastly different from those near the sun. Could a hidden planet be lurking in the darkness? The question lingered, driving astronomers to push the boundaries of observation and theory. As telescopes grew more sophisticated and algorithms for detecting faint objects improved, the search for this hypothetical planet intensified. Yet, despite the growing body of evidence, the mystery remained unsolved. The outer solar system continued to guard its secrets, leaving scientists to wonder what else might be hiding in the vast unexplored expanse beyond Neptune. The hunt for this elusive object became a global endeavor. Teams from the United States, Europe, and Asia collaborated to pool their resources and data, hoping to catch even the faintest glimpse of this hypothetical planet. The Large Synoptic Survey Telescope, LSST, set to begin operations in the 2020s, promised to revolutionize the search by mapping the entire sky every few nights, potentially revealing objects too faint or distant for current telescopes to detect. Meanwhile, the public's imagination was captured by the possibility of a Planet 9. Artists created vivid renderings of what this distant world might look like, depicting it as a cold, icy sphere bathed in the faint light of the sun. Science fiction writers wove tales of expeditions to this hypothetical planet, imagining what its surface might hold: frozen oceans, towering ice cliffs, or perhaps even signs of life adapted to the extreme conditions. The mystery of the aligned orbits had become more than just a scientific puzzle. It was a story of exploration, a quest to uncover the final secrets of our solar system. Speculation. If such a planet exists, it would be a world unlike any other in the solar system. Its distance from the sun would make it one of the coldest places imaginable, with temperatures potentially dropping to 220 to 364 degrees. Yet, it might also harbor unique geological features, such as cryovolcanoes spewing liquid nitrogen or vast subsurface oceans kept warm by the planet's internal heat. The discovery of such a world would expand our understanding of what is possible in the solar system and beyond. As the search continued, astronomers remained cautiously optimistic. The evidence for a hidden planet was compelling, but the solar system had a history of surprising scientists. Just as Neptune's discovery had revolutionized astronomy in the 19th century, the confirmation of a new planet in the 21st century would mark a monumental achievement. Yet, even if no such planet were found, the quest to understand the aligned orbits would continue, driving innovation in observation and theory. For now, the outer solar system remains a frontier of discovery, a region where the known gives way to the unknown. The aligned orbits of these distant objects stand as a testament to the enduring mysteries of the cosmos, a reminder that even in our own celestial backyard, there is still so much left to explore. And somewhere, perhaps, a hidden planet waits to be found, its presence hinted at only by the subtle dance of distant objects in the night sky. Part 3. The Hypothesis of Planet 9. In 2016, two astronomers at Caltech, Konstantin and Mike Brown, took the analysis further. They focused on the 6 most extreme objects, those with perihelia beyond 30 astronomical units and semi-major axes beyond 250 astronomical units. Their findings were staggering. Not only were the orbits of these objects aligned in direction, but they were also clustered in 3-dimensional space. All 6 orbits were inclined about 30 degrees downward relative to the plane of the solar system. The odds of this happening by chance? Less than 0.07%. This alignment was not a subtle hint, but a glaring anomaly, a cosmic breadcrumb trail leading to an unseen force shaping the outer reaches of our solar system. Batygin and Brown likened the probability of this alignment occurring randomly to flipping a coin and having it land on its edge multiple times in a row. The 6 objects in question, Sedna 2012 VP113 and 4 others, are not mere asteroids, but trans-Neptunian objects, TNOs, with diameters ranging from 100 to 1,000 kilometers. Sedna, one of the most studied of these objects, has an orbital period of approximately 11,400 years, while 2012 VP113 takes about 4,200 years to complete its journey around the Sun. These objects are not just distant, they are also incredibly slow-moving, their glacial paths a testament to the vast empty expanses they traverse. Imagine a celestial ballet performed in extreme slow motion, where the dancers, these distant TNOs, are influenced by an unseen choreographer, Planet 9. Batygin and Brown ran computer simulations to test different scenarios. Could this be random? No. Could it be caused by observational bias? No. The only explanation that consistently reproduced the observed pattern was the presence of a massive perturber, a planet orbiting far beyond Neptune, gently nudging these smaller objects into aligned configurations. This unseen planet would act as a gravitational shepherd, its influence rippling through the Kuiper Belt like a stone dropped into a still pond. The simulations showed that without this perturber, the orbits of the distant objects would scatter chaotically over time. With it, the orbits remained stable and clustered, a delicate dance choreographed by the gravitational pull of an unseen partner. The simulations also revealed that the perturber's orbit would be anti-aligned with the clustered objects, a counterintuitive finding that further solidified the hypothesis. This hypothetical planet, dubbed Planet 9, would be a sub-Neptune, a type of world larger than Earth but smaller than Neptune. It would have a core of rock and ice surrounded by a thick envelope of hydrogen and helium. Its surface temperature would be around 47 Kelvin, or 226 degrees Celsius. At that temperature, it would glow faintly in infrared light, but reflect very little sunlight. Its orbit would be highly eccentric, swinging between 200 and 1,000 astronomical units from the Sun, taking between 10,000 and 20,000 years to complete a single orbit. To visualize this, imagine a planet that spends most of its time in the frozen depths of the outer solar system, only occasionally venturing closer to the Sun. At its farthest point, it would be over 20 times the distance from the Sun to Pluto, drifting through a region of space so cold and dark that it challenges our ability to observe it with current technology. If you were to stand on the surface of Planet 9 at its aphelion, the Sun would appear as little more than a bright star, its light too feeble to provide any meaningful warmth. What we know, the clustering of distant objects suggests the presence of a massive perturber. The gravitational influence required to align these objects points to a body with a mass roughly 10 times that of Earth, making it a significant player in the solar system's dynamics. The orbits of these objects are not just aligned, but also stabilized, indicating a persistent and substantial gravitational force at work. Batygin and Brown's calculations suggest that Planet 9's gravitational pull would explain not only the alignment of the TNOs, but also the mysterious 6-degree tilt of the Sun's rotational axis relative to the plane of the planets. But we don't know whether this perturber is a planet or something else entirely. Its exact composition, size, and orbital parameters remain speculative. The mechanisms by which it formed and evolved are still unknown. Did it originate in our solar system, or was it captured from another star system during a close encounter billions of years ago? Some theories suggest that Planet 9 could be a rogue planet, ejected from its original system and later captured by our Sun. Others propose it might be a remnant of the primordial disk of material that formed the solar system, never fully coalescing into a proper planet. Observation. The orbits of the 6 most extreme TNOs are not only aligned, but also exhibit a peculiar clustering in their arguments of perihelion, the angle that defines the orientation of an orbit. This clustering defies the random distribution expected from purely gravitational interactions with known planets. If Planet 9 exists, its gravitational influence would explain this alignment, as well as the perplexing detachment of some TNOs from Neptune's influence. Interpretation. The alignment and clustering of these distant objects cannot be explained by the gravitational influence of the known planets alone. The presence of an additional massive perturber, Planet 9, provides a plausible explanation for these observations. Its gravitational pull would act as an unseen hand, gently guiding the orbits of these objects into their current configurations. Speculation. If Planet 9 exists, it could be one of the most significant discoveries in solar system exploration since the identification of Pluto in 1930. Its detection would not only confirm the hypothesis, but also force astronomers to rethink the formation and evolution of the outer solar system. It could also provide insights into the early dynamics of the solar system, shedding light on the processes that shaped the orbits of the known planets and the distribution of smaller bodies. But what if the clustering isn't real at all? This question haunts the hypothesis, a specter of doubt that lingers in the minds of astronomers. If the alignment of these distant objects is an illusion, a product of incomplete data or confirmation bias, then Planet 9 could be nothing more than a phantom, a mirage conjured by wishful thinking. Yet, the evidence continues to mount. Since Batygin and Brown's initial proposal, additional objects have been discovered with orbits that fit the pattern, strengthening the case for an unseen perturber. The discovery of 2015 TG387, nicknamed the Goblin in 2018, provided further support for the hypothesis. Its orbit, with a semi-major axis of 73 astronomical units, is aligned with the other extreme TNOs, adding another piece to the cosmic puzzle. The hunt for Planet 9 has reignited a sense of wonder and exploration among astronomers. It has inspired new surveys of the outer solar system, such as the Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory, which will scan the sky with unprecedented sensitivity. The LSST, scheduled to begin operations in 2024, will be capable of detecting objects as faint as magnitude 27, far beyond the capabilities of current telescopes. If Planet 9 exists, it may be lurking in the vast unexplored regions of the Kuiper Belt or beyond, waiting to be discovered. Its detection would not only confirm the hypothesis, but also revolutionize our understanding of the solar system's formation and evolution. It would reveal a world that has eluded us for centuries, a silent sentinel in the cosmic night. The search for Planet 9 has also sparked a renewed interest in the outer solar system's dynamics. Researchers are now exploring the possibility that Planet 9's gravitational influence could explain other mysteries, such as the peculiar orbits of certain comets and the distribution of small bodies in the inner Oort cloud. Some have even suggested that Planet 9 could be responsible for the extinction events on Earth, as its gravitational perturbations might periodically dislodge comets from the Oort cloud, sending them hurtling toward the inner solar system. While these ideas remain speculative, they highlight the far-reaching implications of the Planet 9 hypothesis. Yet even if Planet 9 is never found, the search itself has already transformed our view of the outer solar system. It has led to the discovery of new objects, the refinement of orbital models, and the development of advanced observational techniques. It has reminded us that the solar system is not a static, well-mapped territory, but a dynamic, ever-changing frontier. The ongoing exploration of the outer solar system has revealed a region teeming with surprises, from the unexpectedly complex structure of the Kuiper Belt to the presence of distant objects with orbits that defy easy explanation. The hypothesis of Planet 9 is more than a scientific theory. It is a testament to human curiosity, a beacon guiding us into the unknown. It represents our relentless pursuit of knowledge, our desire to understand the cosmos and our place within it. As we continue to explore the outer reaches of the solar system, we are not just searching for a new planet, we are expanding the boundaries of our understanding, pushing the frontiers of science, and deepening our connection to the universe. Whether Planet 9 is real or not, the journey to find it has inspired us to look beyond the familiar, to question the accepted, and to embrace the endless possibilities of the cosmos. Part 4. The Skeptics. Not everyone is convinced by the Planet 9 hypothesis. Some astronomers argue that the clustering could be an illusion, a trick of incomplete data. The outer solar system is vast, and our surveys of it are far from comprehensive. Most telescopes focus on specific regions of the sky, often avoiding areas obscured by the Milky Way or limited by weather conditions. If you only look in one direction, you'll only find objects in that direction. This observational bias, skeptics argue, could create the appearance of clustering where none exists. The debate isn't just academic, it shapes how astronomers allocate precious telescope time and funding. For instance, the Large Synoptic Survey Telescope, LSST, set to begin operations in 2024, will scan the entire visible sky every few nights. If Planet 9 exists, LSST could detect it within its first few years of operation. However, skeptics caution that prioritizing Planet 9 could divert resources from other scientific pursuits. The LSST, now renamed the Vera C. Rubin Observatory, represents a $473 million investment and is expected to generate over 20 terabytes of data per night, making its observational strategy a contentious topic among researchers. The Outer Solar System Origin Survey, OSOS, conducted between 2013 and 2017, discovered over 800 trans-Neptunian objects. When they analyzed their data, they found no clustering among the most distant objects. 8 objects in their survey had semi-major axes greater than 150 astronomical units, but their orbits were scattered in all different directions, no alignment, no pattern. The OSOS team prides itself on its meticulous approach to avoiding bias. They carefully mapped their search areas and ensured that their telescopes surveyed regions of the sky that had been previously ignored. Yet even with this rigor, they found no evidence to support the Planet 9 hypothesis. Samantha Lawler, one of the astronomers working on OSOS, argues that the clustering seen in earlier studies might simply reflect where astronomers happen to be looking. Lawler points out that many of the objects used to support the Planet 9 hypothesis were discovered by the same surveys, using the same telescopes, and focusing on the same regions of the sky. The OSOS survey was conducted using the Canada-France-Hawaii telescope, a 3.6-meter instrument perched atop Mauna Kea in Hawaii. The telescope's location, high above the cloud line, offers unparalleled views of the outer solar system. However, even this vantage point has limitations. The survey's detection efficiency drops significantly for objects beyond 1,000 astronomical units, meaning that a distant Planet 9 could still elude detection. Additionally, the survey's sensitivity to smaller, fainter objects decreases rapidly with distance, leaving a potential blind spot in the data. Despite these challenges, OSOS remains one of the most comprehensive surveys of the outer solar system to date, providing a crucial counterpoint to the Planet 9 hypothesis. What we know, some surveys have found no evidence of clustering. For example, the Dark Energy Survey, which scanned the southern sky between 2013 and 2019, detected no clustering in the orbits of distant trans-Neptunian objects. The survey, conducted using the 570-megapixel dark energy camera mounted on the Victor M. Blanco telescope in Chile, imaged over 5,000 square degrees of the sky. Its primary goal was to map the distribution of dark matter and dark energy, but its high-resolution images also revealed thousands of trans-Neptunian objects. Similarly, the Deep Ecliptic Survey, which ran from 1998 to 2005, found no clear pattern among the objects it observed. This survey, led by the University of Arizona, used the Kitt Peak National Observatory's 4-meter Mayall telescope and discovered over 400 trans-Neptunian objects, including several Kuiper Belt objects with unusual orbits. These surveys, along with OSOS, suggest that the clustering observed in other studies may not be a universal feature of the outer solar system. What we don't know, whether these surveys are missing part of the picture due to observational bias. It's possible that the surveys that found no clustering were simply looking in the wrong places or at the wrong times. The outer solar system is dynamic, with objects moving along their orbits over decades or centuries. A survey that looks at a particular region today might miss an object that was there yesterday or will be there tomorrow. Astronomers are also limited by the sensitivity of their telescopes. Small, distant objects may go undetected, leaving gaps in the data. For instance, A typical trans-Neptunian object with a diameter of 100 kilometers would be too faint to detect at distances beyond 200 astronomical units, even with the most advanced telescopes. Additionally, the gravitational influence of Planet 9, if it exists, might only affect certain types of objects, making its effects harder to detect. Some models suggest that Planet 9's influence could be most pronounced on objects with highly elliptical orbits, which are less common and more difficult to observe. Could the disturbance be a sign of new physics? Some skeptics propose that the peculiar orbits of distant objects might not be caused by a hidden planet, but by exotic physics. One idea is that the collective gravity of small, scattered objects in the outer solar system could create a gravitational stirring effect, nudging the orbits of larger objects into unusual alignments. This concept, known as self-stirring, has been explored in simulations, which show that a disk of small bodies could produce observable perturbations in the orbits of larger objects over billions of years. Another theory suggests that the disturbances could be the result of a dark companion, a primordial black hole, or a clump of dark matter orbiting far beyond Pluto. These ideas, while speculative, highlight the possibility that the outer solar system might be more complex than we imagine. A primordial black hole, if it exists, could have formed in the early universe and been captured by the sun's gravitational pull. Such an object would be incredibly dense, with a mass comparable to that of a planet, but compressed into a space smaller than a city. Its gravitational effects would be subtle but detectable, potentially explaining the peculiar orbits of distant trans-Neptunian objects. Alternatively, a clump of dark matter, the mysterious substance that makes up about 27% of the universe, could exert a similar influence. Dark matter is thought to interact only through gravity, making it invisible to telescopes but capable of shaping the dynamics of the solar system. Observational bias isn't the only challenge facing the Planet 9 hypothesis. Some astronomers question whether a planet as massive as the one proposed could exist so far from the Sun without being detected. At 10 times the mass of Earth, Planet 9 would be a significant object, yet it remains invisible. Skeptics argue that if such a planet exists, it must be incredibly distant, perhaps as far as 700 astronomical units from the Sun. At that distance, even the most advanced telescopes would struggle to spot it. For comparison, Pluto, the most famous trans-Neptunian object, is only about 40 astronomical units from the Sun on average. Others point out that the gravitational influence of Planet 9 should leave traces in the orbits of other objects, such as the giant planets or even the Sun itself. So far, no such evidence has been found. Recent studies have analyzed the orbits of the gas giants, Jupiter, Saturn, Uranus, and Neptune, and found no anomalies that could be attributed to Planet 9's gravitational pull. Despite the skepticism, the search for Planet 9 continues. Astronomers are developing new techniques to scan the outer solar system more efficiently. For example, the Backyard Worlds Planet 9 project invites citizen scientists to help sift through data from NASA's Wide Field Infrared Survey Explorer, WISE mission. Since its launch in 2017, the project has discovered over 1,100 new objects, including several brown dwarfs, stellar objects too small to sustain nuclear fusion. While Planet 9 remains elusive, the search has already yielded valuable insights into the outer solar system's mysteries. One of the project's most intriguing discoveries is the Goblin, a trans-Neptunian object with an extremely elongated orbit that brings it as close as 65 astronomical units to the Sun and as far as 2,900 astronomical units away. This object, formerly known as 2015 TG387, has an orbit that is consistent with the influence of Planet 9, though more data is needed to confirm this. The debate over Planet 9 is a reminder that science is a slow, iterative process. Ideas are proposed, tested, and refined over time. Sometimes, the most exciting discoveries come not from confirming our hypotheses, but from disproving them. In 2019, a team of astronomers led by Scott Shepard of the Carnegie Institution for Science used the Subaru telescope in Hawaii to conduct the deepest survey of the outer solar system to date. The survey, which covered 800 square degrees of the sky, discovered 120 new trans-Neptunian objects, including one with an orbit that suggests it may be influenced by Planet 9. However, the team also found that the clustering of orbits was less pronounced than expected, adding further complexity to the debate. Whether or not Planet 9 exists, the search for it has pushed the boundaries of our knowledge and inspired new ways of exploring the cosmos. As astronomer Carl Sagan once said, "Somewhere, something incredible is waiting to be known." The quest for Planet 9 has already revealed a wealth of new objects and phenomena in the outer solar system, from distant dwarf planets to mysterious gravitational anomalies. Even if Planet 9 turns out to be a phantom, the journey to find it will have expanded our understanding of the solar system's farthest reaches, where the light of the sun fades into the vastness of interstellar space. Part 5. The Gravity of the Galaxy. While the Planet 9 hypothesis has gained traction, other explanations have emerged, challenging our understanding of the cosmos. One of the most intriguing is the idea that the clustering of distant solar system objects could be caused by a modified theory of gravity called MOND, modified Newtonian dynamics. Proposed in 1983 by physicist Mordechai Milgram, MOND was originally conceived to explain the puzzling rotation curves of galaxies without invoking the mysterious and unseen substance known as dark matter. The idea is that gravity doesn't behave quite the way Newton described it at very large distances or very low accelerations. Instead of falling off predictably, gravity remains slightly stronger than expected, subtly altering the dynamics of objects far from the central mass. MOND suggests that beyond a certain threshold, roughly one-third the distance to the nearest star, or about 12,000 astronomical units, AU, gravity's influence deviates from classical predictions. In the vast, empty expanses of the outer solar system, this deviation could be enough to shape the orbits of icy bodies like Sedna and 2012 VP 113, which never come close to the Sun. These objects, known as extreme trans-Neptunian objects, ETNOs, have orbits that are difficult to explain with conventional gravity alone. Their elongated, tilted paths seem to defy the gravitational influence of the known planets, hinting at an unseen force at work. For example, Sedna's closest approach to the Sun is a staggering 76 AU, far beyond the orbit of Neptune, and its farthest point extends to nearly 1,000 AU, well into the realm where MOND's effects might become significant. Imagine Sedna, a reddish, icy world drifting through the cold emptiness of the outer solar system. Its surface, untouched by sunlight for millions of years, reflects the faint glow of distant stars. This lonely wanderer is not alone. Other ETNOs like 2012 VP 113 and Leleakuhonua share its distant realm. These bodies, all with perihelia beyond Neptune's orbit, move through space in a slow, silent ballet, their orbits mysteriously aligned. The alignment points not to a single unseen planet, but to something far grander, the gravitational pull of the Milky Way galaxy itself. If MOND is correct, objects in the outer solar system might be feeling a subtle gravitational influence from the Milky Way galaxy itself. This influence would be too weak to notice in the inner solar system, where the Sun's gravity dominates, but could become significant at hundreds of astronomical units from the Sun. The Milky Way, with its estimated 400 billion stars and a supermassive black hole at its core, exerts a gravitational pull that, while faint, could disturb the orbits of distant objects over billions of years. This gravitational tug could explain why the orbits of ETNOs appear to cluster in ways that defy conventional explanations. The alignment of their orbits might not be due to a single massive object like Planet 9, but rather to the collective influence of the galaxy itself. To visualize this, consider the Milky Way as a vast rotating disk of stars, gas, and dust. At its center lies Sagittarius A, a supermassive black hole with a mass of roughly 4 million solar masses. This immense gravity well tugs at everything around it, including the Sun and its retinue of planets, but its influence extends far beyond our solar system. Like a gentle breeze shaping the trajectory of a feather, the galaxy's gravitational pull could be subtly altering the paths of distant etnos. Over eons, this influence could align their orbits, creating the clustering patterns astronomers have observed. A 2023 study published in the Astrophysical Journal took this idea to the test. Researchers simulated the orbits of etnos under the influence of MOND and compared the results to observed data. The findings were striking. MOND predicts that the major axis of distant objects should align with the direction toward the galactic center. And when they checked the data, that's exactly what they found. The alignment was subtle but statistically significant, suggesting that the gravitational tug of the Milky Way could be shaping the outer solar system. This alignment is not easily explained by the Planet 9 hypothesis, which would predict a different pattern of orbital clustering. The study analyzed 14 etnos, including Sedna 2012 VP113 and Leleaku Honua, all with perihelia beyond Neptune's orbit. Using sophisticated simulations, the researchers modeled how these objects would move under MOND's influence. The results were clear. The orbits clustered in a way that matched the observed data, with their major axes pointing toward the galactic center. This alignment was not random, but statistically robust, with a confidence level of over 95%. The study concluded that MOND could explain the orbital clustering without invoking an unseen planet. Yet MOND is not without its critics. The theory has struggled to explain other phenomena, such as the large-scale structure of the universe or the dynamics of galaxy clusters. Some argue that MOND is a mathematical convenience rather than a true reflection of nature. For instance, MOND struggles to account for the observations of gravitational lensing, where massive objects like galaxy clusters bend the path of light. Dark matter, despite its elusiveness, has a strong theoretical foundation and is supported by a wealth of observational evidence, including the bullet cluster, where the distribution of mass inferred from lensing matches the distribution of dark matter but not the visible matter. The debate between MOND and dark matter remains one of the most heated in modern astrophysics. One of MOND's greatest challenges is explaining the large-scale structure of the universe. Galaxies are not distributed randomly, but form a vast interconnected web of clusters and filaments. This structure is thought to have emerged from tiny fluctuations in the density of the early universe, amplified by gravity over billions of years. Dark matter models naturally explain this structure, as dark matter provides the extra gravitational pull needed to form these massive cosmic structures. MOND, however, struggles to account for this without invoking additional mechanisms. Another key test for MOND is gravitational lensing, where massive objects like galaxies or clusters bend the path of light passing nearby. This effect, predicted by Einstein's theory of general relativity, has been observed in countless systems. Dark matter models accurately predict the amount of lensing based on the observed distribution of mass. MOND, however, often underestimates the lensing effect, as it does not account for the unseen mass provided by dark matter. The bullet cluster, a system of two colliding galaxy clusters, provides a striking example. In this system, the distribution of mass inferred from lensing matches the distribution of dark matter but not the visible matter, posing a significant challenge to MOND. Observation. MOND could explain the orbital clustering without requiring a massive perturber like Planet 9. Its predictions align with the observed alignment of etnos, offering a compelling alternative to the planet hypothesis. MOND also has the advantage of simplicity. eliminating the need for unseen planets or exotic forms of matter. However, it fails to account for phenomena like gravitational lensing, which are well explained by dark matter models. Interpretation. The alignment of ETNOs with the galactic center suggests that the Milky Way's gravity plays a role in shaping the outer solar system. This could mean that the clustering of distant objects is not due to a single massive object, but to the collective gravitational influence of the galaxy. However, MOND's inability to explain other cosmic phenomena, such as galaxy cluster dynamics, weakens its case as a universal theory of gravity. Speculation. If MOND is correct, it would revolutionize our understanding of gravity and the cosmos. It could mean that dark matter, one of the greatest mysteries in astrophysics, is not a physical substance, but an artifact of our incomplete understanding of gravity. However, it is also possible that the true nature of gravity lies somewhere between MOND and traditional models, requiring new physics that is yet to be discovered. Future observations, such as the detailed mapping of ETNO orbits or the study of galaxy rotation curves, could provide the evidence needed to tip the scales in favor of one theory or the other. Imagine a camera panning across a starry sky, the Milky Way's luminous band stretching across the frame. Superimposed on this celestial backdrop are the orbits of distant objects like Sedna and 2012 VP 113, their elongated paths aligned toward the galactic center. The scene shifts to a simulation where the orbits of these objects are shown under the influence of MOND, their paths bending subtly in response to the galaxy's gravitational tug. The camera zooms out, revealing the vast expanse of the outer solar system where the influence of the Milky Way becomes apparent. This is not a story of a single planet, but of the galaxy itself, shaping the edges of our solar system with its unseen hand. What if the disturbance isn't caused by a single object at all? The question lingers, inviting us to consider a universe where gravity itself is more complex than we imagined. As astronomers continue to map the outer solar system and probe the mysteries of the cosmos, the answer may lie not in a hidden planet, but in the fabric of space-time itself. The search for Planet 9, whether successful or not, has opened the door to a deeper understanding of the forces that govern our universe. It has forced us to question not just what lies beyond the known planets, but the very nature of gravity and the cosmos. In this quest, MOND stands as both a challenge and a promise, a challenge to our current understanding of the universe and a promise of new discoveries waiting to be made. Part 6. The Disk of Debris. Another alternative to the Planet 9 hypothesis is the idea that the clustering could be caused by the collective gravity of many smaller objects. Imagine a massive disk of icy debris far beyond Neptune, stretching into the vast uncharted territories of the outer solar system. This disk would contain millions of small bodies, rocky fragments, comets, and dust particles, each one individually insignificant in the grand scale of the cosmos. But together, their combined mass could be substantial, perhaps several times the mass of Earth, forming a ghostly ring of material that orbits the Sun in silent harmony. Over hundreds of millions of years, this disk could gravitationally sculpt the orbits of the objects we see, aligning them through a process called collective gravity, like an invisible hand guiding their paths. This disk, if it exists, would be a relic of the early solar system, a time capsule from an era when the Sun was young and the planets were still forming. This idea was proposed by researchers like Anne-Marie Batygin and Antronik Safilian, who delved into the dynamics of such a system with meticulous simulations. Their work showed that under certain conditions, a massive disk could produce the same orbital clustering that astronomers have observed in the distant Kuiper Belt. The Kuiper Belt, a region extending from Neptune's orbit out to about 50 astronomical units (AU), is home to thousands of icy bodies, including Pluto and other dwarf planets. The advantage of this model is that it doesn't require the existence of an undiscovered planet, a hypothetical world that has so far eluded detection despite extensive searches. Instead, the disk would be made of material that we already know exists in the outer solar system, leftovers from the chaotic birth of the planets, frozen in time and space. These remnants, scattered across billions of kilometers, would collectively exert a gravitational influence, subtly altering the orbits of objects within and beyond the Kuiper Belt. The disadvantage, however, is stability. A disk like this would need to survive for billions of years without being dispersed, a challenge in the ever-changing gravitational landscape of the solar system. The outer solar system isn't isolated. Stars pass nearby, their gravitational influence tugging at the delicate balance of the disk. Every 100 million years or so, a star comes within a few light-years of our Sun, close enough to perturb the orbits of distant objects. For example, the star Gliese 710 is predicted to pass within 1.3 light-years of the Sun in about 1.3 million years, potentially disrupting the Oort cloud and other distant structures. The galactic tide, a relentless force caused by the Milky Way's rotation, exerts subtle but persistent pressure, slowly stretching and deforming the disk over time. These perturbations, though small, accumulate over billions of years, gradually eroding the disk's structure. Despite these challenges, the disk of debris hypothesis offers a compelling explanation for the observed clustering. The Kuiper Belt, the region beyond Neptune, is already known to contain a vast reservoir of icy bodies, including objects like Pluto and Arrokoth. If this region were once more massive, it could have shaped the orbits of distant objects through collective gravity. However, the current mass of the Kuiper Belt is estimated to be only about 1/10th the mass of Earth, far below what would be needed to explain the clustering. This raises the question, could the Kuiper Belt have been more massive in the past, only to lose most of its material over time? Observation. The Kuiper Belt today is a sparsely populated region, but it may have been denser in the distant past. Speculation. If the Kuiper Belt were once 10 to 100 times more massive, it could have acted as a collective gravitational force, shaping the orbits of distant objects before losing material over time. The Kuiper Belt's current mass is estimated to be around 0.1 Earth masses, but models suggest that it may have originally contained up to 30 Earth masses of material during the early solar system. This material could have been ejected during the chaotic migration of the giant planets, leaving behind the sparse population we see today. To test this idea, astronomers turned to computer simulations, recreating the solar system's history in digital form. These simulations suggest that the early solar system was a chaotic place, with planets migrating and scattering smaller bodies in their paths. During this tumultuous period, known as the Late Heavy Bombardment around 4 billion years ago, the Kuiper Belt may have lost much of its original mass. The Late Heavy Bombardment was a time of intense impact events, as evidenced by the scarred surfaces of the Moon, Mercury, and Mars. This period of upheaval could have dispersed much of the Kuiper Belt's material, reducing its gravitational influence. If this is true, the disk of debris hypothesis becomes more plausible. However, the exact mechanics of this process remain uncertain, and more research is needed to determine whether such a scenario could explain the clustering we see today. Interpretation. The clustering of distant orbits could be a fossil record of a more massive Kuiper Belt, sculpted by collective gravity before losing material during the solar system's chaotic youth. The orbits of objects like Sedna and 2012 VP-113, which are detached from the gravitational influence of the giant planets, may be relics of this earlier, more massive disk. Their strange orbits, with perihelia far beyond Neptune, suggest that they were shaped by forces no longer present in the outer solar system. The disk of debris hypothesis also raises intriguing questions about the nature of the outer solar system. If such a disk existed, it would have been a dynamic and ever-changing environment filled with collisions, mergers, and gravitational interactions. These processes could have produced unique objects, such as the recently discovered detached objects like Sedna and 2012 VP-113, which have orbits that never bring them close to the giant planets. These objects might be relics of a once massive disk, their strange orbits a testament to the gravitational forces that shaped them. The orbits of these objects are highly elliptical, with perihelia as far as 80 AU from the Sun, suggesting that they were scattered outward by gravitational interactions early in the solar system's history. However, the disk of debris hypothesis is not without its critics. Some astronomers argue that the current evidence is insufficient to support such a model. They point out that while the Kuiper Belt may have been more massive in the past, it is unclear whether it could have been dense enough to explain the observed clustering. Others question whether the collective gravity of small objects could produce the precise orbital alignment seen in the data. The clustering of distant objects is not perfect. Some orbits are misaligned or have inclinations that don't fit the disk model. These discrepancies suggest that other factors, such as stellar encounters or unseen planets, may also play a role. As with many mysteries in science, the debate continues, fueled by new observations and simulations that push the boundaries of our understanding. What we know. A massive disk of debris could theoretically explain the clustering, and the Kuiper Belt may have been more massive in the past. What we don't know. Whether such a disk could remain stable over billions of years, and whether it could produce the precise orbital alignments observed today. The disk of debris hypothesis remains a tantalizing possibility, but it requires further testing and refinement. Future missions such as the Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory will map the outer solar system in unprecedented detail, potentially revealing new objects and patterns that could shed light on this mystery. The search for answers continues, driven by the fundamental human desire to understand our place in the cosmos. As we peer deeper into the outer solar system, we are not just studying distant objects. We are exploring the history of our own celestial neighborhood. Each new discovery, whether it supports the disk of debris hypothesis or points to another explanation, brings us one step closer to unraveling the story of how our solar system came to be. Part 7. The Primordial Event. One of the most intriguing discoveries in recent years is an object called 2023 KQ-14, nicknamed Ammonite. Unlike Sedna and the other aligned objects, Ammonite's orbit is anti-clustered. Its longitude of perihelion points in the opposite direction. This might seem like a contradiction, but it's actually important. If every distant object we found supported the same pattern, we might start to worry that we were only finding the objects that fit our expectations. But Ammonite shows that the population is more complex than a simple clustering. It's a tantalizing clue that the outer solar system is not as uniform as once believed. With an estimated diameter of just 150 kilometers, Ammonite is a small but significant piece of the puzzle, its retrograde orbit hinting at a chaotic past. Ammonite's discovery was not an isolated event. Astronomers have been steadily uncovering more distant objects, each one adding a new piece to the puzzle. In 2014, researchers identified VP-113, another object with a highly elliptical orbit that never comes closer to the Sun than 80 AU. Its orbit, like Sedna's, is detached from the gravitational influence of the known planets, suggesting an unseen force at work. Since then, the catalog of these distant objects has grown to include over a dozen bodies, each with orbits that defy conventional explanations. For example, Leleaku-Honua, discovered in 2015, has an orbit that takes it as far as 2,000 AU from the Sun, making it one of the most distant objects ever observed. The orbits of these objects are not just curiosities. They are fossils from a time when the solar system was still taking shape. Simulations that include ammonite suggest something fascinating. About 4.2 billion years ago, the longitudes of perihelion of the four known Sedna-like objects may have been tightly clustered. Then, over billions of years, they slowly drifted apart due to differential precession caused by the giant planets. This hints at a primordial event, something that happened early in the solar system's history that elevated the perihelia of these objects and set them on their current paths. Then, over time, the clustering dispersed. This event, if it occurred, would have been cataclysmic, reshaping the architecture of the outer solar system in ways we are only beginning to comprehend. The energy required to scatter these objects into their current orbits would have been equivalent to the gravitational influence of a body hundreds or even thousands of times more massive than Earth. The primordial event, as scientists have dubbed it, remains one of the great mysteries of planetary science. It could have been a close encounter with a rogue planet, a massive stellar flyby, or even the gravitational influence of a yet undiscovered Planet 9. Each hypothesis carries profound implications. A rogue planet, for example, could have been ejected from the solar system entirely, leaving behind a scattered trail of debris. Such an event might explain the existence of Oumuamua, the first interstellar object ever observed, which passed through our solar system in 2017. Its elongated shape and unusual trajectory have led some researchers to suggest it could be a fragment of a larger body torn apart during a catastrophic event. A stellar flyby, on the other hand, would have gravitationally disrupted the orbits of these distant objects, flinging some outward while others were drawn closer to the Sun. The possibilities are as vast as the cosmos itself. Observation. The orbits of distant objects may have been more tightly clustered in the past. Interpretation. This clustering could be the result of a single catastrophic event that occurred early in the solar system's history. Speculation. If such an event occurred, it could explain not only the orbits of objects like Sedna and Ammonite, but also the existence of the Kuiper Belt and the Oort cloud. These regions, teeming with icy bodies and comets, may be the remnants of a violent reshuffling of the solar system's outer reaches. The Kuiper Belt alone contains over 100,000 objects larger than 100 kilometers in diameter, each one a potential time capsule from the solar system's chaotic infancy. The Oort cloud, even more distant and enigmatic, is estimated to contain trillions of comets, some of which may have been hurled into their current orbits during the primordial event. The search for answers has led scientists to push the boundaries of observation and theory. The latest telescopes, like the Vera C. Rubin Observatory in Chile, are designed to scan the sky with unprecedented precision, detecting objects as faint as 24th magnitude. This will allow astronomers to map the outer solar system in greater detail than ever before, potentially uncovering hundreds more objects like Sedna and Ammonite. Each new discovery brings us one step closer to understanding the primordial event, if it exists. The observatory's Legacy Survey of Space and Time, LSST, is expected to catalog over 10 billion stars and galaxies, including millions of objects within our own solar system. This flood of data will revolutionize our understanding of the outer solar system's structure and history. But the quest for knowledge is not without its challenges. The outer solar system is a vast and unforgiving expanse where objects are faint, distant, and slow-moving. It can take years, even decades, to confirm the orbit of a single object. The data must be meticulously analyzed, cross-referenced with simulations, and scrutinized for any inconsistencies. It's painstaking work, but the rewards are immeasurable. Every new object, every new orbit, is a step toward unraveling the solar system's deepest secrets. For example, the discovery of the dwarf planet Eris in 2005, initially thought to be the 10th planet, led to a re-evaluation of Pluto's status and a deeper understanding of the Kuiper Belt's complexity. What we know, the orbits of distant objects may have been more tightly clustered in the past. What we don't know, what caused this primordial event, or whether it even happened. The answers, if they exist, are hidden in the cold, dark recesses of the outer solar system. They lie in the orbits of objects like Sedna, VP-113, and Ammonite, each one a silent witness to the solar system's tumultuous past. As our telescopes grow more powerful and our simulations more sophisticated, we inch closer to the truth. The primordial event, if real, could rewrite our understanding of the solar system's history. It could explain the origins of the Kuiper Belt, the Oort cloud, and even the mysterious alignment of distant objects. But for now, it remains a tantalizing enigma, a question mark etched into the fabric of the cosmos. The ongoing exploration of the outer solar system is not just a scientific endeavor, but a journey into our own origins, a quest to understand the forces that shaped our cosmic neighborhood. Are we on the verge of a breakthrough? The question hangs in the air, unanswered but not unanswerable. Every distant object we discover, every orbit we map, brings us closer to the truth. The primordial event, if it occurred, left its mark on the solar system. It's up to us to decipher it. Part 8. The search intensifies. The debate over the disturbance is far from settled, but the search for answers is accelerating, driven by a new generation of telescopes and technologies that promise to illuminate the shadows of the outer solar system. In 2025, the Vera-C Rubin Observatory in Chile began operations, its dome housing a telescope with an 8.4-meter mirror and the largest digital camera ever constructed for astronomy. A 3.2 gigapixel behemoth capable of capturing images so detailed that they could resolve a golf ball from 15 miles away. Over the next decade, the Rubin Observatory will meticulously photograph the entire southern sky every few nights, generating over 20 terabytes of data per night and creating the deepest, widest view of the dynamic universe ever achieved. Among its many scientific goals, the observatory is expected to discover tens of thousands of new trans-Neptunian objects, icy bodies orbiting beyond Neptune, including potential members of the elusive clustered population that has fueled the Planet 9 hypothesis. If the clustering is real, the Rubin Observatory's unprecedented dataset will confirm it beyond any doubt. If, however, the clustering is merely an artifact of observational bias or statistical fluctuation, the observatory's comprehensive survey will reveal that as well, closing one chapter of the search while opening others. The Rubin Observatory's legacy. Survey of Space and Time, LSST, will not only expand the catalog of known trans-Neptunian objects, but also track their movements with unprecedented precision. By plotting the orbits of these distant bodies, astronomers hope to detect subtle gravitational perturbations that could point to the presence of an unseen massive object, such as Planet 9. Even if Planet 9 does not exist, the LSST will provide invaluable insights into the dynamics of the outer solar system, shedding light on the complex interplay of gravitational forces that shape the orbits of these icy worlds. The observatory's data will also enable researchers to refine models of the solar system's formation, helping to explain how these remote bodies ended up in their current orbits. Other instruments are also contributing to the search, each bringing unique strengths to the table. The James Webb Space Telescope, JWST, launched in 2021 and stationed 1 million miles from Earth, is revolutionizing infrared astronomy with its sensitivity to the faint thermal glow of cold, distant objects. Its segmented gold mirror, spanning 6.5 meters, allows it to detect radiation from bodies as far away as the hypothesized Planet 9, which, if it exists, might emit a faint but detectable signature in the mid-infrared spectrum. Already, JWST has produced stunning images of distant galaxies and nebulae, demonstrating its ability to peer into the farthest reaches of the cosmos. Its infrared capabilities are particularly well suited to studying the outer solar system, where objects are too cold and distant to be easily detected by visible light telescopes. Meanwhile, radio telescopes like the Atacama Large Millimeter Sub-Millimeter Array, ALMA, in Chile, and the Very Long Baseline Array, VLBA, are tracking the subtle motion of distant bodies with extraordinary precision. By measuring the tiny shifts in the positions of background stars caused by the gravitational pull of unseen objects, these instruments are helping to map the invisible architecture of the outer solar system. ALMA, with its 66 high-precision antennas, can detect the faint microwave emissions from cold, dusty objects, providing another avenue for exploring the outer solar system's mysteries. The VLBA, spanning thousands of miles across the globe, uses the technique of very long baseline interferometry to achieve resolutions finer than any single telescope, allowing it to pinpoint the locations of distant objects with remarkable accuracy. Even citizen science projects are playing a vital role, recruiting thousands of volunteers to sift through archival data from surveys like the Sloan Digital Sky Survey and the Pan-STARRS project, searching for overlooked clues hidden in plain sight. One such project, Backyard World's Planet 9, has already led to the discovery of several new brown dwarfs, failed stars that are too massive to be planets but too small to sustain nuclear fusion. These discoveries not only add to our understanding of the solar neighborhood, but also demonstrate the power of crowdsourcing in modern astronomy. By enlisting the help of volunteers, researchers can analyze vast datasets more efficiently, increasing the chances of uncovering hidden gems in the data. What we know: new telescopes and surveys are poised to revolutionize our understanding of the outer solar system. The Rubin Observatory alone will increase the known population of trans-Neptunian objects by an order of magnitude, providing statistically robust samples to test theories about the solar system's formation and evolution. For example, the observatory's data could help determine whether the orbits of these distant bodies were shaped by the gravitational influence of a passing star early in the solar system's history, or if they were sculpted by the migration of the giant planets like Jupiter and Saturn. Meanwhile, JWST and other infrared observatories are pushing the limits of detection, probing regions of the electromagnetic spectrum where cold, distant bodies might reveal their presence. The sheer volume of data being collected, petabytes per year, is transforming astronomy into a big data science, where machine learning algorithms and advanced statistical techniques are as essential as the telescopes themselves. What we don't know: whether these tools will finally solve the mystery of the disturbance. The outer solar system is vast and enigmatic, and even the most powerful telescopes are limited by the laws of physics and the practical constraints of observation. For instance, if Planet 9 exists but is smaller or colder than predicted, its thermal emission might fall below JWST's detection threshold. Similarly, if the disturbance is caused by a more exotic phenomenon, such as a primordial black hole or a collective gravitational effect of smaller bodies, it may elude detection entirely, leaving astronomers with more questions than answers. Some researchers have even proposed that the disturbance could be the result of dark matter interactions, a hypothesis that would require entirely new methods of detection beyond the capabilities of current instruments. Observation. The search for the disturbance has already yielded unexpected discoveries, highlighting the unpredictable nature of scientific inquiry. For example, the hunt for Planet 9 has led to the identification of new trans-Neptunian objects with unusual orbits, such as the distant object nicknamed Far Far Out, which lies over 140 astronomical units from the Sun. These objects, while not yet confirming the existence of Planet 9, are expanding our understanding of the outer solar system's complexity. They also underscore the importance of exploring the unknown, as each new discovery adds a piece to the puzzle of our cosmic origins. Interpretation. The search for the disturbance is not just a scientific endeavor, but a deeply human one. It embodies our innate curiosity and our desire to understand the universe around us. Every telescope pointed at the sky, every algorithm sifting through data, and every volunteer scanning images represents a collective effort to push the boundaries of knowledge. Whether or not the disturbance is explained by Planet 9 or another phenomenon, the search itself is a testament to human ingenuity and perseverance. Speculation. If the disturbance is ultimately traced to an undiscovered planet, it could rewrite our understanding of the solar system's history. Such a discovery would force astronomers to reevaluate models of planetary formation and migration, potentially revealing new insights into the early dynamics of our cosmic neighborhood. Conversely, if the disturbance remains unexplained, it could point to even more profound mysteries, perhaps hinting at new physics or unseen forces shaping the cosmos. Either way, the search for the disturbance is far from over, and its outcome could reshape our place in the universe. What does the disturbance tell us about our place in the cosmos? This question, at once philosophical and scientific, hovers over the search like a guiding light. If the disturbance is the signature of an undiscovered planet, it would reaffirm the idea that our solar system is not a static, well-understood place, but a dynamic and evolving environment. It would also remind us of the limits of human perception and the importance of curiosity and humility in the face of the unknown. On the other hand, if the disturbance turns out to be a mirage, a trick of statistics or observation, it would underscore the challenges of discerning truth in a universe filled with noise and ambiguity. Either way, the search for the disturbance is a microcosm of the broader human quest to understand our place in the cosmos, a journey that has taken us from the caves of Lascaux to the edge of the observable universe. As the search intensifies, so too does our sense of wonder and connection to the cosmos, a reminder that the act of seeking answers is as profound as the answers themselves. Part 9. The Cosmic Perspective. The disturbance in the outer solar system is more than just a scientific puzzle. It's a reminder that our understanding of the universe is incomplete. We've mapped the surfaces of other planets in astonishing detail. Mars's dusty red plains, which stretch for thousands of kilometers, are pockmarked with craters and sculpted by ancient water flows. Jupiter's swirling storms, like the Great Red Spot, have raged for at least 350 years, a testament to the planet's relentless atmospheric turmoil. Titan's methane lakes, filled with liquid hydrocarbons, shimmer under a hazy orange sky, offering a glimpse into a world that mimics Earth's chemistry in alien ways. We've sent probes to the outer reaches of the solar system, with Voyager 1 and 2, launched in 1977, still transmitting data from over 14 billion miles away, their signals taking more than 19 hours to reach us. We've detected thousands of planets around other stars, each one a world with its own mysteries, orbiting suns we can barely comprehend. Some so distant, their light has taken thousands of years to reach us. Yet, despite these achievements, we still haven't finished exploring our own backyard. The outer solar system is vast, cold, dark, and full of secrets. Something is out there, shaping the orbits of worlds we're only beginning to discover. If a massive planet exists beyond Neptune, it would tell us something profound about the history of our solar system. It would suggest that our corner of the cosmos is more violent and chaotic than we realized. Planets, once thought to form in stable, predictable orbits, could instead be wanderers, ejected from their birthplaces by gravitational tugs of war. The Kuiper Belt, a region beyond Neptune thought to contain thousands of icy bodies, might hold secrets of this ancient turmoil. These distant worlds, barely visible in even the most powerful telescopes, could be the debris of a long-ago cataclysm that reshaped our solar system. For example, the scattered disk, a subregion of the Kuiper Belt, contains objects with highly elliptical orbits, suggesting they were perturbed by a massive body in the past, that the architecture we see today is just a snapshot of a system that's been evolving for eons. It would also make our solar system more similar to others. Surveys of planets around other stars, such as those conducted by the Kepler Space Telescope, have found that sub-Neptunes are incredibly common. Nearly every star has at least one. But we don't, or at least we thought we didn't. Finding one in our own system would close that gap, reinforcing the idea that the processes shaping our solar system are universal. Observation. The disturbance, if real, could rewrite the story of our solar system's formation. The orbits of 6 Kuiper Belt objects, clustered in a way that defies explanation, suggest an unseen influence. The alignment of their orbits, tilted 11 degrees from the plane of the solar system, hints at a gravitational pull from something massive and distant. Simulations show that a planet 10 times the mass of Earth, orbiting 20 times farther than Neptune, could explain these anomalies. Yet, despite searches of the sky covering thousands of square degrees, no direct evidence of such a planet has been found. The search has been likened to looking for a single needle in a haystack the size of a city, a task that requires both patience and technological prowess. Interpretation. The cause of the disturbance remains unclear. Some astronomers propose that a dark matter disk, aligned with the plane of the Milky Way, could be warping the orbits of distant objects. This disk, if it exists, would be a remnant of the galaxy's formation, a ghostly echo of the primordial material that coalesced into stars and planets. Others suggest that our understanding of gravity itself may need to be revised. Modified gravity theories propose that the laws of physics as we know them might break down at extreme distances or under certain conditions, challenging our fundamental assumptions about the universe. If a planet is responsible, its origins remain a mystery. Was it formed in place, or was it cast out from the inner solar system during a chaotic phase of planetary migration? And if it exists, why haven't we seen it yet? The search continues, pushing the limits of our telescopes and our imagination. To understand the scale of this mystery, consider the distances involved. Neptune, the farthest known planet, is 30 times farther from the Sun than Earth, its orbit spanning a staggering 2.8 billion miles. Pluto, once considered the 9th planet, is 40 times farther, its surface perpetually shrouded in icy twilight. But the disturbance, if caused by a planet, would originate from a world orbiting hundreds of times farther than Earth. At such distances, the Sun appears as little more than a bright star, its light too weak to drive the processes that sustain life on our planet. Out there, the solar system is a different place, a realm of perpetual twilight, where temperatures plunge to within a few degrees of absolute zero. It's a place where worlds are sculpted not by the warmth of the sun, but by the cold mathematics of gravity. The hunt for this unseen world is not just a scientific quest. It's a journey into the unknown, driven by the same curiosity that has propelled humanity to explore the farthest reaches of our planet and beyond. The search has inspired new technologies such as adaptive optics that correct for the blurring effects of Earth's atmosphere, and new collaborations, like the international teams working on the Large Synoptic Survey Telescope, LSST, which will scan the entire visible sky every few nights. It has reminded us that, for all our advances, we are still a species of explorers, compelled to push beyond the boundaries of the known. And it has shown us that, even in our own backyard, there are still frontiers waiting to be discovered. The outer solar system, once thought to be a barren expanse, is now revealing itself as a dynamic and complex environment. The New Horizons mission, which flew past Pluto in 2015, unveiled a world of stunning diversity. Ice mountains towering as high as the Alps, glaciers of nitrogen flowing like rivers, and a hazy atmosphere that stretches halfway to its largest moon, Charon. Beyond Pluto, the Kuiper Belt teems with worlds of every shape and size, from tiny comet-like bodies to dwarf planets like Eris and Haumea, which spin so fast their shapes are distorted. Each one is a time capsule, preserving the conditions of the early solar system. Each one holds clues to the forces that shaped our cosmic neighborhood. Yet, for all its richness, the outer solar system remains a challenge to explore. At such vast distances, even the fastest spacecraft would take decades or centuries to reach the realm of the hypothetical Planet 9. Voyager 1, the farthest human-made object from Earth, has been traveling for over 45 years and is only just entering interstellar space. A planet 10 times the mass of Earth, orbiting hundreds of times farther than our own, would reflect so little sunlight that it could easily hide among the countless stars of the Milky Way. To find it, astronomers must combine the power of the world's largest telescopes, like the Subaru telescope in Hawaii and the upcoming extremely large telescope in Chile, with cutting-edge data analysis techniques. They must sift through petabytes of data, searching for the telltale signs of a distant world moving against the backdrop of the stars. Speculation. If Planet 9 exists, it could be the key to unlocking the mysteries of our solar system's past. Its orbit, tilted and elongated, might explain the strange alignment of the Kuiper Belt objects, and even the slight tilt of the Sun's axis relative to the plane of the planets. Its presence could also shed light on the formation of the Oort cloud, a spherical shell of icy objects at the very edge of the solar system, which is thought to be the source of long-period comets. Yet, even if Planet 9 is never found, the search itself is a testament to human ingenuity and perseverance. It has pushed the boundaries of our technology, our knowledge, and our understanding of the universe. Will we ever find the truth? The answer depends on our perseverance, our ingenuity, and our willingness to embrace the unknown. But history teaches us that every mystery, no matter how daunting, is an opportunity for discovery. The search for Planet 9 is more than a quest to find a single world. It's a chance to redefine our understanding of the solar system and our place within it. And even if the answer remains elusive, the journey itself will expand the horizons of human knowledge, inspiring new questions and new dreams. For in the end, the true measure of exploration is not the destination, but the courage to set sail. Part 10. The journey continues. The mystery of the disturbance is far from solved, but the journey toward finding the answer is what drives us forward. Science is a process of discovery, of noticing something strange, coming up with hypotheses, testing them, refining them, and gathering more data. The outer solar system is a vast, unexplored frontier, spanning over 9 billion kilometers from the Sun to the theorized Oort cloud. Every new piece of data adds another layer to the puzzle, whether it's the unexpected orbital alignment of distant Kuiper Belt objects, or the enigmatic behavior of objects like Sedna, which never come close enough to the giant planets to be influenced by their gravity. Each observation is a step forward, a glimpse into the unseen. The Kuiper Belt alone, stretching from Neptune's orbit at 30 AU to approximately 55 AU, is estimated to contain hundreds of thousands of icy bodies larger than 100 kilometers in diameter. This region is home to worlds like Pluto, Eris, and Haumea, each with its own system of moons and unique surface features. Pluto, once considered the ninth planet, is now recognized as one of the largest Kuiper Belt objects, with a diameter of 2,370 kilometers and a thin nitrogen-rich atmosphere. Eris, slightly smaller but more massive, orbits even farther out, reaching distances of up to 97 AU from the Sun. These worlds are time capsules, preserving the conditions of the early solar system in their icy compositions and ancient craters. Beyond the Kuiper Belt lies the scattered disk, extending to 100 AU, and potentially the Oort cloud, a spherical shell of icy objects thought to begin at around 2000 AU and extend as far as 200,000 AU, almost a third of the distance to the nearest star, Proxima Centauri. The Oort cloud is believed to be the source of long-period comets, which can take thousands or even millions of years to complete a single orbit around the Sun. Comets like Halley's Comet, with its 76-year orbit, are thought to originate from this distant reservoir, occasionally perturbed by passing stars or the gravitational influence of the Milky Way itself. These distant regions are so far from the Sun that temperatures plummet to near absolute zero, freezing water, methane, and other volatiles into solid ice. Consider the scale of the challenge. The Voyager 1 spacecraft, launched in 1977, has traveled over 159 AU in 45 years and is only just beginning to enter interstellar space. At this rate, it would take over 12,000 years for a spacecraft to reach the inner edge of the Oort cloud. And yet, the mystery is driving us forward, pushing us to look deeper, to build better instruments, to ask harder questions. The James Webb Space Telescope, launched in 2021, is already revolutionizing our understanding of the universe with its infrared capabilities, peering through dust and gas to reveal hidden structures. Its 6.5-meter mirror, composed of 18 gold-plated hexagonal segments, is designed to detect the faintest infrared signals from the earliest galaxies and exoplanets orbiting distant stars. Meanwhile, the upcoming Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory will scan the entire visible sky every 3 nights, generating an astronomical catalog over 1,000 times larger than any previously created. This unprecedented dataset will allow researchers to track the movements of millions of objects in the outer solar system, identifying subtle gravitational perturbations that could point to the presence of an unseen mass. The observatory's 8.4-meter telescope, equipped with a 3.2 gigapixel camera, will capture images with such precision that astronomers will be able to detect changes in the positions of celestial objects as small as a coin viewed from 100 kilometers away. The outer solar system is vast, cold, dark, and full of secrets. Something is out there, shaping the orbits of worlds we're only beginning to discover. The disturbance is real. The cause is still debated. Some researchers propose the existence of Planet 9, a hypothetical world estimated to be 5 to 10 times the mass of Earth, orbiting far beyond Neptune. Its proposed orbit is highly elliptical, with an average distance of 400 to 800 AU from the Sun, and it may take between 10,000 and 20,000 years to complete one revolution. Such a world would be too faint to detect with current telescopes, but its gravitational influence could explain the alignment of certain Kuiper Belt objects and the detached orbits of objects like Sedna. Observation. The orbits of 6 Kuiper Belt objects, Sedna 2004, VN 112 2007, TG 422, 2010 GB 174, 2012 VP 113, and 2013 RF 98, all point to the influence of an unseen mass. Their orbital planes are tilted relative to the plane of the solar system, and their closest approaches to the Sun, perihelia, are aligned in a way that defies random chance. Speculation. If Planet 9 exists, it could be a super-Earth, a rocky world larger than Earth but smaller than ice giants like Neptune and Uranus. Alternatively, it might be an icy giant itself, ejected from the inner solar system during the chaotic early days of planetary formation. Its surface could be a frozen wasteland, bathed in the faint glow of a distant sun, with temperatures as low as 220 degrees Celsius. Other hypotheses suggest the gravitational influence of a dense cluster of small icy bodies, or even the subtle tug of distant stars passing through the solar neighborhood over millions of years. The Milky Way's gravitational field, combined with the occasional close encounter with passing stars, could perturb the orbits of Oort cloud objects, sending some of them plunging toward the inner solar system as comets. These interactions are slow and subtle, playing out over millions of years, but their cumulative effects could explain the observed disturbances. For now, all we can do is keep searching, keep questioning, keep watching the edge of our solar system for signs of what might be hiding just beyond our view. The answer is coming, but it will not come easily. It will emerge slowly, piece by piece, as we refine our instruments, sharpen our theories, and push the boundaries of what we can observe. The European Space Agency's upcoming Gaia mission, for example, aims to map the positions and motions of over 1 billion stars in the Milky Way with unprecedented precision, potentially revealing new clues about the solar system's dynamics. The journey itself is a testament to human curiosity and resilience. The mystery of the disturbance is not just a scientific puzzle. It's a reminder of how small we are in the grand scheme of the cosmos and how much we still have to learn. Every new discovery, from the rings of Saturn to the moons of Pluto, has expanded our understanding of the universe and our place within it. The outer solar system, with its icy worlds and distant mysteries, is the next frontier, waiting to reveal its secrets to those who dare to look. End of transmission.